A summary of all of calculus. Now, without all the little details, here's a statement of the fundamental theorem of calculus, integral from a to b of f prime of x dx equals f of b minus f of a. Now, the usual way this is written, let's just go with the usual way it's written, is to use capital F's. That's fine. Lowercase f's, whatever is fine. I'll just go with the usual notation here. And there's conditions about what function needs to be continuous and stuff like that. But let's not worry about that right now. The fundamental theorem of line integrals said that the line integral over the curve C of the gradient of a scalar function f, which is itself now going to be here a vector field, dot dr. That this is going to be f of r of b minus f of r of a. Look at how similar that is really to the fundamental theorem of calculus. We saw Green's theorem, which said that the double integral over d of quantity partial derivative of q with respect to x minus partial derivative of p with respect to y dA equal the line integral over c of p dx plus q dy. Another way to state the same, so these are really the same, it's just in different notation. We could have the double integral over d of curl of a vector field capital F, then dotted with k dA. And on the other side, we'll have the integral over, just to change up the notation and get a couple things going here, the boundary of d, which should be a closed curve, f dot dr. Now, how does this fit what we have just one line above? This happens if f is the two-dimensional vector field with components capital P, capital Q. So that's how we get this to match up with the notation from the previous line. Now, we have Stokes' theorem, which can be stated the integral over the surface S of curl of a vector field F dot d bold S, or S with an arrow as we have here, and that's going to equal the integral over the curve C, which is the boundary of the surface, of f dot dr. But to get this to look more like what we have here, the second way that Green's theorem was written, we can also write integral, double integral over the surface S of, and then we'll just insert parentheses here, just for clarity's sake. They're not really going to be needed. So curl of f dot n d plane S, just trying to make it look a lot more like this. So the dot k is like the dot n of, on the other side, this line integral, so boundary of S, f dot dr, and this is what happens if capital F is equal to P, comma, Q, comma, R. So look at really how similar these two lines are from each other. We have the divergence theorem, which was triple integral over E of the divergence of f dv is equal to the double integral over the surface S, which is the boundary V, of f dot d bold S. So this is the book's notation for the flux. We could also write this as triple integral over E of the divergence of f dv, and have here, instead of a capital S, we'll just, to make some connections here, we're going to put boundary of E, and then just change how this is written as f dot n d plane S. Now, either way that this is written, here or here on the right side, this is the flux of the vector field F across the surface S. Oh, meant to mention earlier, here these parentheses, they're helpful to have, but they're not strictly speaking necessary, right? Because if you had curl of I should write it directly in any. If you had curl of and then f dot n as if the dot product should be performed first, that'd make no sense because then what's there would be a scalar. You can't take the curl of a scalar. So that's why the parentheses here, you don't have to draw them, but I think maybe they're visually helpful to draw in any case. Now the thing to notice about what you see on this side over here, every single one of these on this side, the left side of each one of these, is the higher dimensional integral, right? So triple integral here versus double integral. Double integral here versus single integral. Double integral versus single integral. The other thing is to mention that it's on this side, on the left side, that there's a mention, there's a mentions the derivative. So here it's divergence, here it's curl, here there's partial derivatives written, curl again, gradient, or just a prime itself. I mean, really all of these things, whether it's f prime, or it's the gradient of f, or it's the curl of a vector field, or it's the divergence of a vector field, all of these things involve performing some kind of derivative or partial derivative. Then on the other side, so on this side, to the right side of each of these equations, well then that's the lower dimensional thing, right? So it's one dimension lower. In other words, there's one fewer integral sign written because you're integrating over an object that's one dimension smaller in size. So here you had triple integrals, here you have double integrals because you're integrating over a surface, which is really a two-dimensional object living in three-dimensional space, a flat object in three-dimensional space. Here you have double integrals, and here you have single integrals because you're integrating over a line or really a curve. So a curve is truly a one-dimensional thing, even if that one-dimensional creature, a string, lives in two- or three-dimensional space. Here you have single integrals, so you have to have one fewer integral sign over on this side. These, you could sort of say, well, you could call those things, if you'd like, they're really zero-dimensional integrals right here and here. Right? So based on what we're seeing here, these are zero-dimensional integrals in a sense, where if one-dimensional is line-like, then zero-dimensional is point-like. And look, you evaluate f at 2 points. Here you evaluate f at 2 points. And then the other thing about the right side in each case is that the integration is on the boundary, right? Which is what this notation boundary of E, boundary of S, boundary of D is really all about. Even in the fundamental theorem of calculus itself right here, if we go back to Calc 1 and think of drawing a picture of how to represent that, you've got some function here. This is your f prime of x that you end up integrating. So this capital F prime of x is this f prime of x that appears in the integrand, and you integrate from a to b. We often talk about this as just being the area under the curve in a sign sense, and that's fine, right? It is that. But the thing to note is you could instead think of it like you have this number line from A to B, and at each point on the number line, I mean at literally each point on the number line, here and there and there and there, the value of f prime at each of these spots is something like, right at that point, there's a little leprechaun, and then if the number, the value of f prime at this point here is positive, that's how many coins, that the chocolate coins that the leprechaun throws to the right. If the number is negative, that's telling you how many coins the leprechaun throws to the left. And then what you have on this side, the right side here, well, it's really, we could say that this is -1 times f of A plus 1 times f of B. It's just writing f of B minus f of A in sort of a different order. Why do this is because f of B, it's right. What we're saying is there's a certain flux going across the boundary. The boundary here of the interval See, you integrate from A to B, you're talking about the interval from A to B. And so then the boundary itself consists of just these 2 points. And so the flux this way, if we orient outward, that's why there's a 1 here. But if we take this point here, we need to orient, the sort of a one-dimensional version of flux here in the other direction, leftward. And that's why this is a minus, right? Because the left moving from to the right of A over this way, that left is outwards here. Actually, what happens, and you don't need to worry, I mean, all of this is meant to try to review and collect everything together. In the end, though, all of these theorems, I mean, really all of the theorems you see here, all of these are encapsulated in what's called the generalized Stokes theorem. So if you integrate over a manifold and you have this, don't worry too much about the notation here, just, you will not be responsible for this in this class. But this is a generalized notation to really cover all of the derivative notations you see in here. This ends up being the integral over the boundary of that manifold. We'll just call it a shape of this omega, this thing that looks like lowercase w of this omega itself. Now the number of integral signs here, we don't know what size, what dimension m is. So that's why to state this theorem, people just tend to draw one integral sign alone. So there's a general theory in which all this fits, in which this theorem is introduced. This theorem should probably deserve a better name, but for lack of one, it happens to be called the Generalized Stokes theorem. We don't have the tools here right now to prove this or anything like that. It's involved, and this leads to a whole other area of math which you've seen a couple allusions to, called topology. Anyway, this one theorem, if truly understood for what it's trying to say, it ends up as special cases having all of these theorems that are mentioned or summarized here in these equations.